Hi. Today we're going to talk about air pollution and the effect that humans have had on particles, chemicals in the air, and how that has affected the environment. And to be more specific, our agenda is to talk about air pollution, different kinds of air pollution, anthropogenic air pollution. We're going to specifically talk about acid rain and how that has come about and the effect that that has on the environment. And then we're going to talk about the ozone and why ozone is important and what human activity has done to destroy the ozone layer. And this is a module that I enjoy speaking about because it's rather optimistic. With regards to ozone specifically, humans have done a lot of mitigation to prevent or to stop the damage that they're doing and to try to prevent future damage from occurring. And we'll look at some data that demonstrates that the steps that we've taken to reduce the damage that we're exerting has actually worked. So I think this is a good module to show what steps we can take to prevent environmental damage and how successful these steps are. So what is air? What is it composed of? Air is composed mostly of nitrogen, and the nitrogen is in the form of N2, two nitrogen atoms linked to each other. So you might remember N2 from our previous module regarding nutrient cycling. The second largest component of air is oxygen, and then there's a lot of other gases that take up a very small percentage of the air you breathe. So mostly nitrogen. Earth's atmosphere is composed of multiple layers, and these layers differ from each other with regards to how far they are from Earth and the temperature, and at times they have different compositions of different gases. The troposphere is the layer that's closest to Earth, and it goes about 10 miles above where you're standing now. The stratosphere is above the troposphere, and this goes from about 10 to 30 miles. Let's look at a graphical representation of the different layers of the atmosphere. And what I want you to notice is here we are at the very bottom here in the troposphere. This is us standing on Earth way down here, and this is moving up in altitude as we go farther and farther away from Earth. And we can see right above us, right above the troposphere, is the peak ozone layer. So we're going to talk about the ozone layer later on in this module. And then we have the stratosphere and other spheres. And one thing that kind of interests me is if I look at the temperature of the ambient temperature at different levels. So here on Earth we're about 30 degrees Celsius, 25 or 30 degrees Celsius, right? That's about room temperature. As we go towards the ozone layer, the temperature drops, and then it increases a little bit and drops again, and then goes very, very, very hot. And that temperature dropping actually here around where the ozone layer is actually due to the presence of ozone. So ozone is causing that temperature drop. So I imagine that you probably have some idea of what kind of chemicals we put up into the air. If you've seen any smokestack releasing a cloud of gas, or cars or trucks, or even particulate matter from a construction site, these are all contributions to air pollution. So any chemical or particulate matter or even microorganisms that are found in the atmosphere at a concentration that's high enough to harm plants or animals to alter the ecosystem. And air pollution can also come from natural sources. So there are actually, when we talk about the ozone layer, we talk largely about the effect humans have had on the ozone layer, but there are also natural sources of chemicals that destroy the ozone. So we're not the only one. We're the majority of the effect that that there is on air pollution, but there's also other natural sources. But we're going to focus on the anthropogenic sources. So natural sources of air pollution might include volcanoes, lightning, forest fires, which can occur without human influence. Plants can contribute to air pollution, and what are the major air pollutants? So specifically when we look at smoke and exhaust, what are the actual chemicals that are destroying the air quality or having a negative effect on the environment? Sulfur dioxide is a really big one, nitrogen oxides, carbon oxides, particulate matter, so any kind of dust or debris that goes up into the air, volatile organic compounds, so these are the main chemicals that affect the ozone layer. Ozone itself is an air pollutant, and it's very important for you to understand the difference between ozone as a pollutant and ozone in terms of the ozone layer that we would like to protect. So when ozone is a pollutant, when it's released somewhere around our level in the troposphere, right, the layer that humans live in this layer, ozone can be a pollutant and can have a hazardous effect on your health. Ozone in the ozone layer, right, 10 or so plus miles above Earth, is completely different than the ozone pollution that occurs on Earth here, down here. So keep in mind that those things are not to be compared. Lead and mercury, and lead is actually, I'll show you in a graph that lead is actually starting to be on the downfall in terms of a pollutant. So what are some things that we do to contribute to air pollution? Mostly vehicles, a lot of on-road vehicles, a lot of burning of fossil fuels contributes to air pollution. Power plants, so creating energy, creating electricity is a huge source of air pollution. Industrial processes, disposal of waste. I appreciate that this table is kind of small, but I'll leave it in the slide so that you can take a look at the different chemicals that contribute to air pollution, and it's going to discuss the effects and impacts of every single chemical. So we will talk in this module about sulfur, about the volatile organic compounds that affect the ozone. Pretty much we'll focus on those two. And so in addition to these chemicals that come about through burning fossil fuels, through running our automobiles and creating electricity, particulate matter is that other kind of nebulous type of air pollution that we discuss. So that can be, again, from natural sources like volcanoes, fires, fossil fuel burning, so all of that particulate matter kind of just goes up into the air, and people have different definitions of what size it should be. So here they're showing you the relative sizes of the particulate matter, and again, it's kind of a nebulous term. We will talk specifically about sulfur and VOCs and the effect that they have, but particulate matter is also a big source of pollution. Okay, so when you drive your car or have a power plant that is burning something to produce energy, you are putting something up into the air. So for example, you're putting CO2 or SO2 or CO, which is carbon monoxide, and that is the primary pollutant. That's going to go up into the air, and that's the direct result of the emission. That might have some kind of chemical reaction once it's in the air, and might turn into something else that might be actually more toxic than the primary pollutant itself. So when these chemicals are chemically converted into another form up in the air by either UV light or some other chemical process, so they will be termed secondary pollutants. So secondary pollutants are transformed in the presence of sunlight, for example, water, oxygen. So the presence of some of these chemicals is just going to alter some chemicals into another form. So sunlight, so UV light, for example, just breaks the bonds between chemicals and turns them into something else. And ozone, sulfate, and nitrate are the secondary pollutants, so they started as one form. So for example, they might have started as carbon monoxide, and then when UV light hit that carbon monoxide, it might have reacted with other carbon monoxides and created ozone, for example. So secondary pollutants such as ozone, sulfate, and nitrate were originally a different molecule, but when UV hit them, they reacted with other molecules, other atoms, or other molecules up in the atmosphere, and were transformed into the chemicals they are now, these secondary pollutants. And typically, these secondary pollutants are the chemicals that are actually exerting some kind of damaging effect. So here's a graphical representation of these primary pollutants, SO2, NO, NO2, CO2, and once they are up in the air, they might be converted into other types of chemicals that might be more toxic than they were originally. And again, I'd like you to see that here in the secondary pollutant, they're showing you O3, and that is ozone. However, this is not the ozone that we talk about when we refer to the ozone layer. This is an ozone pollutant that is closer to us on Earth here. So here are some measurements of the contributors to air pollution and the human activity that has contributed the most to specific kinds of primary pollutants. So if we look at the top one or two activities, it looks like on-road vehicles, right, burning of fossil fuels to drive our cars around. That's a big primary pollutant for carbon monoxide and nitrogen oxides. For sulfur dioxide, generating electricity is a big contributor. And for particulate matter, road dust, miscellaneous activities, industrial processes, etc. So when we think about what we can do individually, I think driving a more fuel-efficient car or using less electricity is what pops out to me from this graph here. So like I said in the beginning of this movie, air quality is somewhat of an optimistic topic when we talk about environmental impact of human activity and restoration of our air resources. So if we look at lead and ozone, for example, we can see that they are starting to get lower and lower and closer to zero, closer to the national standard since the year 1990. So we were polluting with lead very heavily, and human regulations and practices have reduced the amount of lead that we have in the air. So that's kind of a happy story. We've really improved on that realm. So smog might be something that you're familiar with, especially if you're from Southern California. I think people here are relatively aware of smog and have encountered it before. And smog forms when sunlight, nitrogen oxides, and volatile organic compounds are present. So the combination of all these three things creates a chemical reaction and creates smog. So one thing, just as an aside, one reoccurring theme here is that UV light is causing chemical reactions and affecting the nature of chemicals. And UV light is also going to be a topic that we discuss when we talk about the ozone layer. Here is a graphical representation of how photochemical smog occurs. So if we look at the bottom half, we see some nitrate was present in the air, and then there was some sunlight, and the sunlight contributed energy to this chemical reaction occurring, and in this case we can get ozone. However, in the presence of volatile organic compounds, we can also get other compounds to occur given certain chemical reactions, and then this creates smog. Another thing you might be familiar with if you're from LA, for example, possibly other cities that are in a valley and are prone to thermal inversions, is this phenomenon where you actually have a layer of smog kind of resting on the city because of the way the city is positioned in a valley and just the nature of hot air rising. A thermal inversion is when a relatively warm layer of air covers a layer of dense cold air below. and this traps all of that pollution, that smoggy air underneath it, and that smoggy air is not able to leave and go, be taken somewhere else by wind or go higher into the atmosphere. Here is a graphical representation of that. So during the day, this valley is relatively warm, and warm air rises. So the air that's containing all of those smog creating chemicals are going up with the warm air, and they're being taken away by wind, hopefully, and leaving the area. At night, that there is warm air that's created a pocket because warm air rises, and this traps cool air underneath it because we no longer have the air being warmed down there because it's nighttime. And so all of the smog and that cool air is going to be trapped because cool air is going to sink down and not float up because cool air is denser. So that's going to trap a layer of smog in that valley there that's going to stay there. And sometimes you're able to see that if you look at Los Angeles from a distance. Alright, so that's the background of air pollution. That we've talked about several types of air pollution and a little bit about primary and secondary pollutants, and we've talked a little bit about chemical reactions that occur and how mostly they're directed by sunlight, right? Sunlight is contributing energy for these chemical reactions to occur. Now let's talk specifically about acid deposition and what leads to acid rain occurring. So how does air pollution lead to acid rain? So acid rain is caused mostly because of sulfuric acid. So where does the sulfuric acid come from? It comes from the primary pollution, nitrogen, sulfur oxides, and also nitrogen oxides to some extent. And these are released into the atmosphere. So the sulfur oxide goes into the atmosphere. It has a chemical reaction, much like the other chemical reactions we've talked about before. And it reacts with oxygen and water, and it turns into something else. So from sulfur oxide, it becomes sulfuric acid. So now it's a very strong acid. If you've heard of sulfuric acid, you know that's something that you generally want to avoid. And now that it's sulfuric acid, it can break down further into sulfate, and it will actually fall next time it rains. Let's take a step back and talk a little bit about what it means to be acidic or basic, since we're talking about acid rain. So acidic just means that there's more hydrogen ions in the solution, and when that makes the solution acidic. So if you think about a lemon is more acidic than an avocado, and that's simply because there's more hydrogen ions in that solution or in that fruit. So this is just for your edification if you're interested in the chemistry of it. So if we think about water has 2 hydrogens and 1 oxygen, and sometimes that hydrogen molecule leaves. So every once in a while, here's our water molecules, and here's our H's and our O's, right? H2O is water, and sometimes a hydrogen ion leaves and hops onto another molecule, or sometimes doesn't hop onto another molecule. And if all of the H's and all of the O's are in equal concentration, so this solution is considered neutral. But if we start adding additional hydrogens into that solution, it's going to turn it into an acid. So an acid is any substance that increases the hydrogen ion concentration, and we can show that by the letter H. So if we increase the hydrogen ion concentration, that's going to be an acid. If we reduce the hydrogen ion concentration, that's going to be a base. So a lot of detergents are bases. So here's approximately the scale that we're working with when we look at the pH scale. And pH is just a measure of these hydrogen ions. So it goes from 0 to 14, and numbers that are very low are very acidic. So here we have on the low end, we have battery acid, lemon juice, gastric juice, which is the fluid in your stomach. So If you've ever had acid reflux, you know that when that fluid comes up, it's very acidic. Other acidic solutions such as grapefruit juice or soda also are low on the pH scale. So when you think about pH 3 or 4, you're thinking of you're thinking of acidic solutions. Once we get towards 7, that's the neutral zone. So there, the amount of hydrogen ions equals the number of base molecules, and we consider that not to have any free hydrogen ions floating around, so it's neutral. And your blood is pretty much neutral. It's about 7.4. So there we have that on the map there. As we go into higher numbers, we start seeing more and more basic solutions, so bleach, ammonia, some other strong cleaners, oven cleaner. Those are very, very basic, and they work by having that kind of chemistry. So pH is really important for living organisms. If you take your blood pH, which is about 7.4, and change it by even 0.1 pH levels, that's going to have a dramatic effect on your health. So if you go from 7.4 to 7.5, you're going to be one sick cookie. And really, if it goes much higher than that, you're going to pretty much be in the hospital experiencing organ failure. And at some point, about 0.5 pH units away from where your blood pH started, you're going to not be able to survive that. So pH has a pretty significant effect on human health and also the health and survival of other living organisms. So now that we understand the pH scale and we know about hydrogen ions and that the presence of hydrogen ions makes things more acidic, let's take a look at acid deposition again. So here's our primary pollutant. We have sulfur dioxide coming out of, looks like in this case, some industrial complex or some factory that's generating electricity. And we have this chemical reaction happening in the air. So we're going to change these primary pollutants into secondary pollutants. And this is going to be some chemical reaction that happens in the air in the presence of water and oxygen, like we discussed previously. So that changes it into sulfuric acid, for example. And then that undergoes another reaction. Here we have sulfate, and we can see here the H pluses, these hydrogen ions, are now floating around loose, and that happened as the result of this chemical reaction. That was the leftover, or that was the chemical reactant that occurred, that resulted here. So what's going to happen now? When a rain cloud forms and there's some precipitation up in the air, those hydrogen ions are going to combine in with the water and come down with the water. And now that water is going to be more acidic, because we know now when we add more hydrogen ions to a solution, it makes it more acidic. So that is how acid rain comes about. And rain pH is normally about 5.5, somewhere there. And we can see on this map that there's a lot of regions in the United States where rain is becoming more acidic than what it is normally. So we have some green areas where we're looking at 5.5, 5.3. In the west of the United States, we have pH levels of the rain closer to the pH level that we would expect. And then on the East Coast, we do see a lot of regions that are becoming more acidic, where the rain is becoming more acidic. So this has a dramatic effect on living organisms. So just recall that if you change your blood pH by 0.1, you are going to probably need to see a hospital right away as soon as you can. So think about what a difference of one whole pH level, right? If we just change you by 0.1, your blood by 0.1, you're going to be very sick. Think about how much one whole pH level might affect the environment. So here's just some pictures showing you acid precipitation. In the upper left, we have just another cartoon of how it works, right? We have sulfur and nitrogen oxides coming from generating electricity and from cars, and these undergo some kind of chemical reaction in the air, and the hydrogen ions result from that chemical reaction come down with the rain, And here they're showing you the dramatic effects that can have on wildlife and vegetation. So plants don't tolerate large changes in pH either. So you're going to be killing off plants as well. So the effects are, if we write this out, is first and foremost, the pH of water might change. So the pH of the ocean is changing, partially because of acid rain, partially also because of a lot of excessive extra carbon dioxide that we're putting into the air. And the ocean is actually absorbing that carbon dioxide. And that decrease of pH, that increase of hydrogen ions in these bodies of water is going to kill off aquatic species in the ocean, so we're going to see a loss of diversity. And we talked about why diversity is so important in that diversity module. So we need that diversity to maintain genetic fitness of a lot of these species and to contribute to variability in the species that we have. Reducing the pH of the water mobilizes metals found in soil, so it's gonna, all of that acid is going to start reacting with metals and other compounds in soil, and it's going to change them and release them into surface waters. We might even have damage to buildings and monuments because of acid rain. So here's a picture of a monument that we might want to preserve, but acid rain might actually destroy. Okay, so controlling these types of pollution, so we saw in those original graphs that the largest contributor by far on that bar graph was burning fossil fuels and generating electricity. So those are two things that as mankind we need to work on reducing our dependence on fossil fuels, reducing our burning of coal when we create electricity. We can also do other things to reduce the amount of pollutants that we put into the air by filtering them out when they're being generated. So a catalytic converter, for example, in a car is filtering out a lot of the air pollutants that might otherwise go into the air. So it's just capturing it before it makes it out there. And there's other physical barriers such as that we can use to prevent air pollution from getting out there and causing destruction.